In this section, we're going to be integrating the natural log function, and it probably makes sense that we're going to use as the basis the differentiation because it's kind of the opposite idea. In the last section, we talked about the derivative of ln x is 1 over x, and it's understood here that x is greater than 0. Now that's kind of implied by the nature of ln x. If ln x makes any sense, since we can only take the natural log of positive numbers, if this makes sense, then x has to be positive. So at any rate, this sort of disclaimer is in here, and I'm pointing it out because of what's going to happen a little bit later. Anyway, we take this situation and we're going to kind of work it in reverse in order to integrate. So I'm just writing these on opposite sides, so we have 1 over x equals the derivative of ln x. Now let's integrate on both sides. So the integral of 1 over x dx, now undo derivative, so we get ln x plus a constant. Now notice the absolute value here. It's kind of necessary in this situation because if we're starting with 1 over x and we're going to integrate the 1 over x, then we would like to be able to integrate this situation whether x is positive or negative. And in order to guarantee us that the ln x part is going to make sense, we just apply that absolute value idea. Now, from a conceptual standpoint, we know that we have to go about matters like this because the general power rule simply doesn't work in this circumstance. You know, we can rewrite this as x to the negative 1. And if we're thinking about the general power rule, remember there was a disclaimer in the general power rule. It said that we'll use that power rule as long as the exponent is not negative 1. You see, so it applies in all cases except this one. And the reason it doesn't apply is because if we tried to apply it, we would get, well, let's see, increase this by 1 so we get we get 0, and then in the denominator we get 0. And that 0 in the denominator is the big problem here. Well, at any rate, so we have a way of integrating, and we'd like to generalize the idea. This is a very specific idea of a single variable, but what if we have an expression that's written in terms of x? And it's the idea of, in the last section we were talking about the derivative of ln u, where u is a function of x. And it turns out to be 1 over u du dx, or the derivative of u with respect to x. Now this notation is fine. There's another notation I think that's a little bit cleaner than this. If we understand that du is u prime dx, imagine replacing the du with the u prime dx. The dx notations would go out and we would have u prime over here and then u prime over u. So I kind of like this kind of notation for it because it's really easy to see and to manipulate. Well, at any rate, let's swap these around and then take the integral on both sides. So the integral of the u prime u dx is ln u plus c. Now notice it's ln absolute value of u. And another way to, if we backtrack on this, this kind of notation, this u prime dx, if we backtrack on that, it's du over u. So either way we look at it, it's okay. Let's take a few problems. We're looking to see that pattern of the u prime over u, and here we're taking the integral of 1 over 6x plus 1. Well, is the 1 the derivative of 6x plus 1? Well, no, we need a 6 up here, and we resort to some trickery. We'll multiply by 6 times 1/6, then we'll put the 6 in this numerator and the 1/6 out here. And now we have the u prime over u idea, and it's real easy to see through. So that integral then is natural log of the absolute value of the denominator. And that's really all there is to it. So it's 1/6 natural log of the absolute value of the denominator plus a constant. Here's another one. And again, we're just looking for that u prime over u idea, and we're asking ourselves, is this the derivative of that? Well, let's see. The derivative of 3x would be 2x squared. The derivative of x cubed would be 3x squared, and we have that up here. The derivative of x would be 1. So yes, we do have the condition that we need, and so it's the natural log of the absolute value of the denominator plus a constant. Here's another one. we've got now look for the derivative of the denominator. The derivative of the denominator needs to appear in the numerator for us to apply this definition, this idea. So let's see, the derivative of 2x, of x squared would be 2x. Well, we only have an x here, we need a 2 factor. The derivative of 2x would be 2. Gee, we need a 2 here. So we need to multiply in the numerator by 2. We can do that again by multiplying by 1/2 times 2, put the 2 inside, the 1/2 outside, and we have the condition that we need. So this is 1/2 the natural log of the absolute value of the denominator plus a constant. And this applies to trigonometric functions as well. Here we see tangent x in the denominator. The derivative of tangent x is secant squared x, so we have the conditions that we need to take the integral. So this is the natural log then of the absolute value of the denominator plus a constant. Here's one that requires a little more manipulation. Notice that we just have 1 in the numerator and we have these 2 factors in the denominator. I'm going to kick the x to the 2/3 to the numerator and write it as x to the negative 2/3. And now, because of the complication, we might go into the substitution idea, thinking of this as u and investigating for u prime. So we're going to substitute or think about x to the 1/3 plus 1 as u. Now u prime then, see, we can work with the idea of u prime kind of as a separate from looking at this. Now we may be able to see through it like this and we may not. It really doesn't make a great deal of difference here, I don't think, but I want to show you how this routine works out. So the u prime, let's see, the derivative of x to the 1/3 is 1/3 x to the negative 2/3. Well, that's nice because we have the x to the negative 2/3 already up here. We just need the 1/3 factor, and this kind of reminds us of that. And so we'll pop in the 1/3 factor here and a 3 out here, and then we're ready to go. Now we have the conditions that we're after. It's u prime over u dx, and so it's 3 times the natural log of the absolute value of the denominator plus a constant. Now, about right here in the development of this problem, we could actually physically make the substitution. I didn't actually make the substitution here. I used the substitution in order to figure some things out about the 1/3 and the 3. But I could actually make the substitution here, and the substitution I would make would come from taking this expression and kind of solving it for the numerator. How can I replace here for the numerator? And I would do that by multiplying on both sides by 3. So I would have 3u prime equals x to the negative 2/3. In other words, 3u prime equals x to the negative 2/3. Now, with that, I can substitute back into the expression before, and the x to the negative 2/3 numerator becomes 3u prime. And then the denominator was the u. And now, since I'm looking for the u prime over u situation, I'll just take this numerator factor, this constant, and kick it to the outside. And now I have the conditions that I want, so it's 3 natural log absolute value of denominator plus constant, back substitute for u, and I have the answer that I got before. Now this method is, I think it's a little bit cleaner than the other method, and it's a method that we'll need to use in other problems in the future. But sometimes it's just a little bit longer, a step or two longer. We're going to look now at a couple of nuances in this process, and these nuances are taken care of by particular manipulations. Let me show you what I mean. Here we have a situation where we're taking the integral, and we notice that the degree of the polynomial numerator is the same as the degree of the polynomial denominator. Now, in this circumstance, we can't possibly achieve or see right away that we have a u prime over u condition. So to manipulate it, to change it into some other form that might meet our requirements, one thing we could do is perform long division. That is, anytime the degree of the numerator is the same as or higher than the degree of the denominator, we can resort to this kind of manipulation. So I'm dividing x squared plus 1 into the numerator polynomial, and you remember this process, x squared into x squared goes 1 time. We put the 1 up here. Usually we try to line up terms of the same degree, so I would put the 1 over here, 1 times x squared, and then 1 times 1, 1. draw the line and subtract, and we had ways of doing this, but when we subtract these, they go out, we bring down the x, and so x is the remainder because it is of a degree lower than the x squared. Okay, so the complete answer in this situation is 1 plus the remainder over the divisor. So it's really 1 plus x over x squared plus 1. Now we can rewrite this then in this form. So it is the integral then of 1 plus x over x squared plus 1. And now we can sort of separate our problem into sort of two integration problems. Let's take it from up here. Here's the same step that we had below. So it's the integral of 1 dx, or just dx. The 1 is in here just for emphasis, but plus the integral of this fraction dx. And now we can apply this idea of the u prime over u, and this we can handle from our previous experience. Well, here we're looking for the u prime over u situation, and the derivative of x squared is 2x, so we need a 2. So we apply an outside 1/2 factor and then an inside factor of 2, and we have the conditions that we need. So this part becomes 1/2 natural log. It would be absolute value of x squared plus 1 plus the constant, but we don't really need absolute value here because it's guaranteed that this value will be positive because of the x squared. Okay, at any rate, and here the integral of 1 dx is simply x. So that's one situation that we can apply in this matter of integration. And you know, when you first bump into a problem, when you first look at a problem in integration, you're not sure that whether or not we're going to be using this idea of natural log. If you were looking at a battery of problems and you were taking them at face value, then you would bump into the situations that cause you to apply this idea of natural log. Now, and because of that, use the manipulative processes that we have encountered before and just see what you bump into. When you bump into the circumstance of the u prime over u, or the 1 over x, then that's when you're applying this idea of natural log. Here's a problem that involves another nuance. It's 2x over x plus 1 all squared, and we're taking the integral. Now, I'm using as u the x plus 1. Now we're not, let's say that we're not expecting to run into the natural log idea, the idea of the integration of the 1 over x or the u prime over u. But we may run into it. And that's the way we need to view the situation. It's not the case that even though we're in a section that deals with this, it's not the case that every problem will have that situation occur. So let's just go through and follow our nose through here and perform a substitution. U is x plus 1. Well, du is 1 dx. Now I'm using a du notation here because I'm going to completely go into the substitution form here, and I'd like to use du rather than have a dx sticking in there. But gee, with the du is 1 dx, these are pretty much interchangeable, aren't they? But at any rate, we need a substitution in this numerator. You see, we don't have a sort of a natural substitution in the numerator here, so we need to solve this for x because we'll need to replace the x with something in terms of u, and that's kind of built in here. Solve this for x, we have x is u minus 1. So now we can write the expression as 2 times u minus 1 with this substitution, and then since u is the x plus 1 in the denominator, it's u squared in the denominator, and I can write this as du. So a rather clean kind of notation here. Now the 2 we can just yank out of the whole process and consider this. We can make this into two fractions, u over u squared minus 1 over u squared, kind of like this. And now we can reduce here and rewrite here. So let's do that up here. We have remember that 2 was outside of the integration symbol, so we have 2 times the integral of 1 over u du, and then minus 2 times the integral of u to the negative 2 power. And we just look around to see, oh, well, here we are using that idea that we talk about, the natural log idea. So it's 2 natural log absolute value of u, and then over here minus 2 u to the negative 1 over negative 1, and we can clean this up a little bit. The negative negative becomes positive, and this is 2 times 1 over u. And then we just do a back substitution. U is x plus 1 in both cases, and we're done. On this one, we want to solve the differential equation. Dy over dx is 2x over x squared minus 9. Now, to solve that differential equation, we're going to integrate, and we can manipulate here into dy equals 2x over x squared minus 9 dx. And if dy is this, then y is the integral of that. So we're taking the integral of this, and it works out rather nicely here because this numerator is the derivative of the denominator. Then we have the u prime over u condition that we're looking for. So y then is the natural log of the absolute value of the denominator. We don't need the absolute value, though, because we have the x squared involved. Or maybe it's more accurate that we have the x squared involved and we don't have a first degree x term in order to cause this to possibly become negative. At any rate, x squared plus 9 and then plus the constant. Now, you know, with differential equations, this is really a family of equations. If we construct the graph of this, we would have to set a value of c. And if we change the value of c, then the graph would tend to either rise or fall in its same pattern on the coordinate plane. So in order to cause that graph to fall in a certain position, we can actually predetermine a point that will occur on the graph, and then we can solve for c. Here's what I mean. Suppose we want the graph of this differential equation to go through the point 0, 4. Well, we would do this. Let me back up over here. Now here's our sort of rather broad general form. The one that we just calculated is y is ln x squared plus 9 plus c. And we would like for the graph to go through the point 0, 4. Now, in order for the graph to go through this point, we have to set a specific value for c to cause that to happen. Now, to determine the value of c, since we have coordinates that are in the x, y form, we replace x with 0 and y with 4. So 4 then is ln 0 squared plus 9. Here's what we're doing. Now we're going to solve this for c. This is natural log of 9. So this is 4 minus ln 9 equals c. And if c has this value, I can take this value and put it in this position. So it becomes y equals ln x squared plus 9 plus the c value 4 minus ln 9. And this, the graph of this should go through the point 0, 4. Let's take a quick peek at the graph. Here's the function as we had it on the board just a few moments ago, and the graph looks like this. We can just about see by observation that the graph goes through the point 0, 4, but we can tell for sure if we press trace, and here the coordinates at the bottom are indeed 0, 4. From what we already know, definite integration is rather predictable. Here we have, we want to integrate on the interval from 0 to 3, this expression, and we are looking for the y prime over y condition, and the derivative of the x squared is 2x, so we need a 2. We pop a 2 in here and a 1/2 outside, and away we go. So the integral here is the natural log of the absolute value of x squared plus 1. We don't need the absolute value because of the x squared, and the limits of our integration. So we just pop in those limits. It's when x is replaced with 3, we have 3 squared 9 plus 1, 10. So this is ln 10 minus, and when x is replaced with 0, we have ln 1. We know that ln 1 is 0, so this goes out. We have 1/2 ln 10, which is approximately 1.51. We can make an interpretation in terms of area here if we want to, but this is the calculation of the definite integral. Now, we can cause those, or sometimes those nuances come into play. The nuances that we talked about a little bit earlier come into play in a situation involving definite integration like this. We have the integral from 0 to 1 of this. Now notice the degree of numerator and denominator is the same, so we go into this process of long division. X plus 1 into the x minus 1, gx and x goes 1 time, 1 times x, x, 1 times 1, 1. And then when we subtract, we change the sign here and collect, and this becomes -2. So the remainder is -2, so the complete answer is 1 plus -2 over x plus 1. Certainly we could write this minus sign right here. It doesn't make any difference. But at any rate, we can replace this expression with that expression, and now we have something that's a little more meaningful. We can kind of distribute this idea of integration. The integral of 1 dx plus the integral of this expression dx is what we're talking about. And the integral of the 1 is highly predictable here. The -2 can just come to the outside, and I've written that up here. Notice the -2 outside the integration symbol. And now we have the u prime over u condition here, and the integration here is simply x. So this becomes the x, and this is -2 ln absolute value denominator and the limits of integration. And now we just pop in those limits. When we pop a 1 in place of these x's, we have 1 minus 2 ln 2. When we replace the x's with 0, we have, let's see, 0, and then 0 here gives us ln 1, but ln 1 is 0, so this whole term goes out. And we have 1 minus 2 ln 2, which is approximately that value. Let's talk about trig functions a little bit. We already know that the integral of sine x is negative cosine x plus a constant, and the integral of cosine x is sine x plus a constant. And there are some obvious situations where the integration is rather predictable. If we know that the derivative of tangent x is secant squared x, then the integral of secant squared x would be tangent x plus a constant. So those kinds of things are rather predictable, but we can actually generate a rule or a formula involving all of the other trig functions directly. That is, we want to think about the integral of all of the 6 trig functions. We have the first 2 right here. Let's talk about tangent and cotangent because they're pretty easy to develop sort of from scratch. If we're thinking of the integral of tangent x dx, we just think about tangent as being sine x over cosine x, and then try to create the u prime over u condition. The derivative of cosine x is negative sine x, so we need a negative sign here. We pop it in here and then outside, and now this becomes then negative natural log absolute value of denominator plus a constant. And the integral of cotangent x is even easier. Cotangent x is cosine x over sine x, and since the derivative of sine x is cosine x, we have the condition that we're looking for. So this is the natural log of the absolute value of the denominator plus a constant. Now, I'm not going to go through the algebra involved with secant and cosecant. I'll just give you the formulas. You can look at these. I think either one or both of them are in your textbook. But there's a little more algebra involved, and I don't think it's worth us going through all of that process here. But I'll tell you what they are. The integral of secant x is the natural log of the absolute value of secant x plus tangent x plus a constant. And you can read for yourself what the integral of cosecant x is. Now, to use these, sometimes it's helpful to think about these formulas in this way. Now, secant x dx is equal to all of this. Now, we can think, though, in terms of, let me just replace this with u. You see, this also applies to secant u du as being equals natural log absolute value secant u plus tangent u plus a constant. And it's helpful to think about it this way when we're looking at a problem like this. You see, we have the integral of secant x over 2 dx. Now we're thinking of the u as the x over 2. So let's see. Now, you know, there are several right ways to think about this. And if you're thinking about it a little bit differently than I do here, that's perfectly all right, probably. I can't show all the different ways to do this correctly, but I just want you to know that there are variations on this theme that can be applied here. You know, it's that u prime idea and that du idea, you know, using those different notations gives you a little bit different look in the development of this kind of problem. But you know, if you stick to one form or another, that's fine. If you can move from into different forms, that's okay too. But just realize that there are different ways to do this correctly. Now the du here is, now remember this is 1/2 x, so du is 1/2 dx. Now if du is 1/2 dx, now look at over here what we have. We have secant u dx. Now let's solve that for dx. That's one technique, that's one way to do the substitution in this successfully. Now if we're solving this for dx, we would have 2 du is equal to the dx part. Now so then we'll go back into this and make the substitution, and it'll look something like this. So we have secant u, and then the dx part is 2 du. So we have 2 du. You see, and I'm emphasizing that substitution. And now this 2 can just kick to the outside. So we have 2 integral secant u du. And now we're in the condition that we have up here to go through that formula, you see. So it's 2 ln, and then from the formula up there, it's absolute value of secant, and it's secant u plus tangent u. But at the same time that I go through and write this, I can back substitute for u. Remember, u is the x over 2, so it's secant x over 2 plus tangent x over 2 plus a constant. Way back when we first learned about the idea of derivative, and we generated derivative functions, that derivative function was a way for us to calculate the slope of the tangent line of a function very quickly. That's what derivative is all about, isn't it? And now we're at a point with integration at our disposal where we can start with a derivative function such as this one, and we can generate the original function. And that original function is the antiderivative function associated with this one. And we talk about, in a sense, we talk about this process as solving for a differential equation. And actually it's a family of differential equations. And if we have a certain point associated with that family of differential equations, then we can identify the specific one that goes through that point. Okay, so all of that is just background for what I'm about to tell you. It turns out that if you have a derivative function like this, that it isn't really necessary for us to find the antiderivative function and then construct its graph for us to know a great deal about the behavior of the graph of that antiderivative function. And the reason that we don't need to generate that function and look at its graph is because we have plenty of information right here in order for us to discuss and analyze the behavior of the graph of that antiderivative function. Let me show you what that's all about. It involves direction fields. And to generate a direction field, you just take solution points on this derivative function. Now that's what this is. This table of values, these are just solution points for this. All right, so as such, then we could construct the graph associated with this. That's one thing we could do. Or we could interpret this table of values as being points associated with the slope of a tangent line on the antiderivative function. So at the point -2, the slope of the tangent line of the antiderivative function is 6.5. At the point -1, the slope is 3. At the point 0, the slope is 0.5. Now, interpreting like this as slope values, then what we can do is say, gee, we don't know where the graph of the antiderivative function goes through the coordinate plane exactly, but we know its slope at -2. So what we can do is, over here on a coordinate plane, at -2, we don't know where vertically the graph of the antiderivative function is going through, but we do know that the slope at -2 of the graph of that function is 6.5. So it might be here that the slope is 6.5, it might be there, it might be there, it might be there, and so on. So I'm just writing that slope of 6.5 for all of these vertical values, all of these values you see at -2. And for -1, the slope is 3, so I just angled it over a little bit and made slopes that are approximately 3, and then at 0.5, so I made those, and so on. And then for all the other points, I did the same thing. Now, the value of a direction field like this is that we now have a pretty good picture of the behavior of the graph of the antiderivative function. And we know that because although we don't know where the function goes through, and actually I should say there is a family of functions, we don't know, we can identify a particular one if we pick a certain point on this direction field and say, we want the graph to go through this point. But without that, we don't know how it's justified vertically, but we do know its behavior, because from over here, if we say, for example, that, let's say that the graph starts right here. Well, it has a slope of 6.5 right here, and that's pretty steep. So it's going up in a rather big way, and then the slope becomes 3, and then the slope becomes 0.5, and then, it's angled over right here, so apparently the graph does something like this, and then it comes down, and then you see all I'm doing is paralleling those slope, those little slopes that I have on the direction field, and so I know that the graph of the antiderivative function has this kind of behavior. Now, it turns out that the TI-86 graphing calculator has the ability to construct direction fields. And I'd like to show you that, and occasionally in your textbook you have direction fields illustrated at the ends of sections in the problem set, and you're asked to perform certain tasks and so forth. I want to make sure you understand where those direction fields come from and how they are related to the derivative function and the antiderivative function. Here's a look at the direction field that we were referring to on the TI-86. And here's a look at the graph of the function that corresponds with that direction field. And as we jump back and forth between the two, it's pretty easy to see that we can tell a great deal about the behavior of the graph. Even though we don't know the equation for the graph, we can tell a great deal about it just by looking at the direction field.